All right, hello everyone. So sorry for the late recording of the session. So what happened was I overslept the session, so I woke up a bit late, so I could not join at that time. So now I've decided to just record it myself and I'll upload it to YouTube along with the code, so you can check it out later. So this is the second part of our previous session. So I checked the last week's recordings for your lecture and I found out that you have studied probability, etc. But the professor has decided to cover the coding part in the next week. So we'll delay exercise on that part and we'll continue our exercise on the central tendency. So I'll continue with that. So starting out, we'll use the California housing data set. In this data set, the data looks something like this. You have the different aspects for a particular property, like what is the median income of of those people that live there, how old is the house, what are the average number of rooms, bedrooms, population in the area, average occupation, and similar data sets. So the first thing is that we would like to import it. So we're just connecting. Yeah. So with that, let's move into the first question. The first question says, load the California housing data set, calculate the mean, median, and mode for the median income column. And finally, based on the difference between the mean and the median, what can you infer about this thing? So we have already loaded the data set. So let's compute our mean and the median for median income. So our data frame is DF. We can write DF dot um, median income dot mean. If we first check that, so this gives us the mean, we can try the median, and then we'll have the mode. Right, so if we check mean, median, mode, um, you would notice that the first two are numbers, but if we just print, let us say we have the median, we have the mean, but the mode is actually a series. Okay, so this happens because you can have a bimodal population where you have multiple modes, for example, even in this case. So we'll take the first one. So we have our first mode and then you can print this. That is, um my column is medium income, and for that we can use an f string and we can say my mean is this much, my mode, maybe median first. My median is this much, and the mode is like so. We print this and we have this. So another thing is that these numbers can be really long, and if you would like to format it, the way you do it is after in your curly braces, you include a colon followed by dot 4f. So dot 4f essentially says that I want 4 floating points after my decimal. So if I try this, it says 8707. It will round it for you. So you can do the same thing here. So we get something like this. So in this case, we can again include it for our own sake. So we get 4 of each. We can delete this part. Now for this part, based on the difference between the mean and the median, you will notice that the mean is 3.87, but the median is slightly less, 3.53. So what are the implications of that? I would like you to think about this, and when I upload the notebook to GitHub, you can find the answer there to cross check whether your understanding is correct or not. So continuing with that, we have the next question, which says, focus on the house age column, calculate its range, variance, and standard deviation. So the housing age is like this, 41, 21, 52, etc. So again, take a minute to, pause the video, try it out yourself, and then you can carry along. We have DF house age. This is our column. To identify its range, we essentially need the difference essentially max minus mean. So we need these two terms. So we'll get the max like this. We will get our minima like this, and we can store it as age underscore range is equal to this. To we could essentially rewrite it again and again, but we could also solve it by saying maybe house age is equal to this much, and we can reuse this for. Okay, so we have our age range. Next, we need the variance. So we have age variance, house age variance. So we can straight away use variance, and age std is house age dot std. And then again, we can print this using our f string. That is, my house age looks like this. My range is age range. My variance is age variance. And my STD or standard deviation is age standard deviation 0.4f. And we have these. So 51, this and this. Okay. The last part says, if you were to compare the spread of house age across two different districts, why might you prefer standard deviation rather than variance? So you have two metrics for the spread. You have the variance, you have standard deviation. Suppose you have it for two districts in California. Why would you use standard deviation rather than using variance? So that's another question for you. The third part says, calculate the coefficient of variation for both median income and population. Which variable shows higher relative variability, and why is CV more useful than STD when comparing two specific questions? So first, what exactly is our COV? COV, or the coefficient of variance, is essentially your standard deviation normalized by your mean, and you can convert it into a percentage by multiplying it by 100, or you can leave it as is. Okay, so if we calculate the um, STD first, we will have STD income is equal to DF medium income dot STD. This is the first thing. We will have our STD for my population, which is DF EOP population dot STD. Now to calculate the coefficient of variation, or just CV, we can just divide it by this. So we will have STD underscore income divided by DF medium income dot mean. We could actually separate this part too, but that's fine. Multiplied by 100, we do the same thing for population. Okay, so we have these two, and then we can print both of these. We can say that my CV of medium income looks like CV income is like this, followed by CV of population looks like this. Okay, and we can maybe print the standard deviation too to compare. So we have STD, uh, STD. Okay, so you would notice that when you have the medium income, you have a CV of 49 compared to a CV of 79. So CV population, CV income, and you have a standard deviation of this much compared to standard deviation of this much. So based on this, the questions are, Why is CV more useful than STD when comparing these two specific variables? So essentially, if I give you these two things, I give you the CV and I give you the STD, which one will you prefer to judge which variable has greater variation? The other thing is, what will you do when the mean is zero? So CV depends on the fact that you have to divide it by the mean. You have to normalize it by the mean. So suppose your mean is zero. What happens to CV in that case? The next question is, consider two distributions. Suppose you have two Gaussian distributions that are identical except for the mean. So suppose one of them has a mean of 1, another has a mean of 10. Okay, identical distributions, just the mean is different. When you normalize them by their means, clearly the CV, that is the coefficient of variation, will come out to be different. So should that be the case? Should your CV be different? And if it is different, what does that imply? For two identical distributions to have different CVs. Okay, so think about that. And again, the answer to these questions will be in the notebook that will be uploaded later. The fourth question, moving on, is quartiles. So how do you identify the first, second, and third quartiles for the average number of rooms in your column? So what does quartile mean? Quartiles essentially means you divide your population into four parts. You have 25%, you could do 50% and you have 75%. So you essentially say, what is the point below which 25% of my data lies? What is the point below which 50% of my data lies? What is the point where 75% of the population lies? So suppose you have a class, like you go to school, you have a class and there are students. Once you have the results, what is the score below which 25% of the students have scored? What is the score below which 50% of the class lies? And what is the score below which 75% of the class lies? This is what essentially quartiles do. So if we have to identify the quartiles for our case, how can we do that? For this, you have to use something called NP dot percentile. Okay, you would notice that this is the same thing as the percentile that you must be aware of. That is, instead of percentage, you can say I got this much percentile. When a student says that I have 90% percentile in my class, he's essentially saying that I have scored more marks than 90% of the class. So for percentile, you're saying I want the percentile for the average number of rooms. Now you have to specify which percentiles do I need. I want the 25th, the 50th, and the 70th percentile. We can print this. So you would notice it's an array. The first number is this, the second number is this, the third number is this. Okay. We can also store these. We can say Q1, second quartile, third quartile. These are my three quartiles. We need the interquartile range. So IQR is equal to Q3 minus Q1. And again, we can print these. I have my column average rooms and my Q1 is equal to Q1 dot 2F. What did we miss? This, we can just copy paste this part. Q2, Q3. So we have Q2, Q3. If we print this, we have 4.44, 5.23, 5.85. We could also print the IQR. My IQR is this much. Okay. So 25, 50, 75, Q3 minus Q1. These are these. So if we move on, is anything left? Calculate the IQR. Explain why it's more robust compared to standard range. That is, if instead of the IQR thing, if I gave you the max minus the min, that is for the total population, the difference between the maximum score and the minimum score is this much. Why is an IQR a better measure compared to the range of your population? Again, the answer I'll be posting it on the notebook. So the fifth question is related to Chebyshev's theorem, which says that according to the theorem, at least 75% of the data should fall within two standard deviations of any distribution. So you can pick any distribution, Gaussian, Poisson, or any random distribution, even uniform, etc., etc. Any distribution, at least 75% of your data should lie within two standard deviations of the mean. So can we verify this empirically for one of our columns? So suppose we go for the median house value column. Can we verify whether 75% of the data lies between two standard deviations? So you have to break your problem accordingly. So the first thing would be to calculate the mean and the standard deviations. Then we will have to calculate how much data lies between these two standard deviations, what percentage does that make, and then we can verify whether it is correct or not. Okay, so starting with we could, for the sake of convenience, say that the mean will be mu and the standard deviation is just STD, or we can again say sigma. My STD will be sigma, and then we say mu is equal to df dot median house value dot mean. My standard deviation is df median house value dot std. And the final thing is, I mean, let's first print maybe this much. Med house value is the name wrong. Med house value. Okay, what are we doing? I think we deleted part of our data now. Okay, so we were here. Df dot columns, we have med house value. So med house value, yep, that works. So we need the mean, that is our mu. We need the standard deviation, or we can say sigma is equal to df med house value dot std. Suppose we print this, we have mu and we have sigma. So we have these two values. The next part is to compute the data that lies between your two standard deviations. So we need the lower half and we need the upper half. So our lower and higher can, or we can say lower and upper, is equal to mu minus two standard deviations and mu plus two standard deviations. Okay, so these are two values. You can also write them separately if you like. We have these. Then we need to identify um, how much data lies between these two things. So essentially, you have to filter out the data between lower and upper. Essentially, you have to mask this part out. Okay, so you need to create a mask. You would remember in the last class, we did something like this. For example, df age is greater than, we can even write on this one. So we have df median house value. This is our column. If we say, suppose, is less than 10, this thing returns a mask, true or false. This is a binary mask, and you can apply it to filter out data. Okay, so we need to create a mask out of lower and upper. So how do we do that? So we have two parts to our mask. Our mask should accept values higher than this lower bound, and we should accept values lower than the upper bound. Okay, so we have essentially two masks. So how do you do that? You have first, let's say mask one is equal to, or you can say mask lower is equal to df median house value is greater or equal to lower. Similarly, mask underscore upper is equal to df median house value less than upper. Now, how do you combine these two masks? Okay, so in Python, you would have noticed that people use, let's say, if, how can we write it? Suppose if condition one and condition two, then you do something. This does not work in this case. Okay, the and that you just saw, or an or, let's say between condition 1 and condition 2, it works when you have these singular conditions. In this case, this whole thing is a series. This whole thing is again a series. Okay. So when you combine these two masks, you have to do an element wise logical and between them. So the way you do it is, instead of using and, you have to use a symbol, this and percent. So this essentially combines two Boolean conditions, but this combines two Boolean conditions element wise. That is, if you have an entire series of them. So if we print these out, if you would notice, mask loaded, we not run it. Yeah. So you would notice that we have 1, 2, 3, 4. All of these are essentially binary conditions. We have to map two of these together. Okay. So in such a case, to create a combined mask, you can say mask is equal to mask underscore lower and mask underscore upper. Okay. If we run this, suppose we do a head here and we do a head here too, you would notice, for example, that the first one is true, the second one is false. If we print our mask here, you would notice that the first one is false, because true and false make a false, but the rest true, 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 the others are also true. So you have combined these two masks. Now you can apply it. So to apply this mask, we just have to do, within our two standard deviations, we have df mask. Okay. And then we can say what percentage do we have here? We can say percentage is equal to length of within two STD. So essentially, when you have, let's say, a DF, length of DF gives you the number of rows. Okay. Another way to do it is DF dot shape 0. That gives you the same thing. So length of my DF, that is my total. I can divide this by length of my full data frame. Okay. And multiply this by a percentage to get this. And then suppose we print this, we get 93%. JB Chef says that you should have more than 75%. We have more than 75%. So this empirically validates our theorem for this particular column. We can write it in a better fashion. We can say print percentage within two standard deviations is percentage point to F, and Jeb requires greater than 75%. Okay. So if you try, for example, mask lower and mask upper, you'll get an error, because it will say the truth value of a series is ambiguous. As I said, using these and or statements verbatim, A and D, that only works if you have a single condition, not a series. So moving on, we get to skewness. Calculate the skewness coefficient for the population using SciPy So I think Pandas does not natively support calculation of skewness. So you have a particular stats. So there is a different library called SciPy. You would notice you have NumPy, you have SciPy. So NumPy is numeric Python. This helps you work with matrices. But if you want to go more into maths, then you use something called SciPy. Okay. So these are three libraries that are often intertwined: NumPy, Pandas, SciPy, is Matplotlib. So you can just import from SciPy, import stats, and then you can just apply it. That is df my population. We can from scipy dot stats import skew. We can say calculate my skewness. If you print this, you get this number. Okay. So you can store this. That is my population skew is equal to this much. Print population skewness is this much. Is this much. Okay. If you go to SciPy and then you go to the documentation, developer guide, API reference would also work actually. Yeah, so you would notice that you have many things, clustering, differentiation, integration, it's linear algebra, etc. We use SciPy Within SciPy you will find a lot of things like cosine, exponentiation, logarithms, etc., etc. So you can just skim through this, and whenever you need something, you can just pick it up from here. So the next question says that no, so it said based on the result, for example, 4.94, classify this as a positively skewed, negatively skewed, or a symmetric distribution. Okay. So up until now, we have been playing with numbers. That is whether something is skewed, what is your interquartile range, etc., etc. Can you visualize it? Suppose you have a meeting with your stakeholders and you have to present that is my data is skewed. They may not essentially understand these numbers, but they may understand it visually. So can you present the skewness? That is, can you present the skewness of your population? So the way to do it is we saw it in the last class. That is, you have df population. You can just call plot on this, and you can say kind is equal to hist. So this is essentially our population. We have this. We have this. To improve this, we can say my x label should be population population. This already says this thing, and I would also like a title, uh, population skewness. Okay, and we could also, I believe, mention a fixed size is equal to, let's say, 10 by 6, right? So we have something like this. You would notice that even though the data essentially lies here, it may seem like there is no data in all of this part. Like after 10,000, it's a waste of space. But actually, there is data all the way up to this point. So it's a tail heavy population, but you can barely see it because essentially everybody is here. Most of the, I mean, houses that we have are below 5,000 in terms of their population, but we still have this part. But if you show it to someone, he'll essentially not know that there is something here. So when you have such a data, such a highly skewed data, you use something called a log scale on the y-axis. So log scale essentially, instead of using this, it will use logarithms of that, and the scale essentially doubles, triples, and so on, instead of saying like 20, 2,500, 5,000, 7,500. So how do you convert your y scale into a log y scale? It is actually pretty easy. You just go here, and then you can say that is my plt dot y scale. I want it to be a log scale. And you would notice that this time we can even see data all the way up to 3,000, 35,000. Okay. And the y-axis has changed. It starts from 0, jumps to 10, goes to 100, goes to 1,000, goes to 10,000. Okay. So it increases by an order of 10 in this case by using a log scale. Okay. And one more thing, it's more of an aesthetic thing, that is our bars are not differentiated by any rows. You can also, I mean, do that. You can specify that I want an edge color. My edge color should be black, and you can now have bars like this. You can play along with this. Yeah, again, we can do this here as well. Edge color is black. You can even use a shortcut like edge color is gray. That's the same thing. Gray is a short for black. Okay, so we have this, we have this. What else? Let's maybe try this. Maybe it will take y scale here. Y scale, yep, it takes it here. So we can specify that I'd like this thing. That doesn't work. Okay, so we have this thing. So suppose you are presenting to someone and you want to show that my data is skewed rather than showing this, maybe you can supplement it by this. That is okay. We have population, and essentially my population at 3,500 is at this, and the usual population is 4 orders higher. So you can also, I mean, use this language here, that is 1 order, 2 order, 3 orders greater than this for magnifying the scale. Finally, we have something called, I mean, we check the interquartile distance. Okay, so this is for the skewness, but the skewness does not say, I mean, essentially show you the outliers. One of the uses of using the quartiles thing, those Q1, Q2, Q3, is that you can use interquartile distance to identify outliers. Okay, so when you use interquartile distance, the way you define outliers is anything outside your 25 percentile, and 75 percentile is an outlier. That is, most of my data should lie between these two things. Okay, so essentially what you do is outside those quartiles, you create something called whiskers. Okay, which are essentially related to what we did earlier, that is two standard deviations, etc. So how can you create that plot? Suppose we want to do the same for medium income. We can say df medium income. We again do plot. We can say kind is equal to box. If we plot this, you would notice that it will create this line. This is your median. You have a box. This box, this lower half is the 25% quartile. This is the 75% quartile. And these are your essentially your whiskers. Okay. What are whiskers? You can check that part out. I believe it is two standard deviations. Whiskers in a box plot. Mm, 1.5 times the IQR. Yeah, so not standard deviation. So you got calculate the IQR 1.5 times on either side is your whiskers. So again, this feels a bit squished. You can essentially modify this. You can say, I rather than having this vertically, I would like it horizontally. So you can say vertical is false. Now you have it like this. You can add a title. You can add a x-axis, etc. So I can say in the title, box plot of median income, net income. So we have this. What else? What else? Maybe we can write in the X label that this is income in USD 10K units. And finally, to avoid this axis thing, you can say pld.show. Okay, so essentially your box plot says that most of your data lies here, and there are a lot of outliers in this part. So what does that mean? So this is essentially telling you the well-known fact of the privileged few. That is, even though majority of your population is here, there are a lot of, I mean, there is a small group of people here that hold a lot of wealth compared to your major population. Like most of your population lies here, but there are people that are super wealthy, like millionaires, billionaires, etc. So this plot essentially answers that part. So I believe that is all. I will, for those who are new to this lecture, the recordings essentially will be on our page, NPTEL, this one. So you'll see the other one here. And again, you'll also see it on GitHub. I will upload it in one of the repos here. You will also see it here. So thank you for your time. See you next week.